Namaskar, I am Naresh Chandrapant, a professor in Department of Geology, University of Delhi. Today, we are going to talk about scanning electron microscope. Why we use a microscope is essentially to characterize geological material. When we characterize a geological material, by that I mean that we try to differentiate the heterogeneities of that material. It can be done using a normal polarizing optical microscope. However, there is a limitation to the polarizing microscope. The limitation is on account of the probe which we use. The probe in a polarizing microscope is light, which has a wavelength ranging from 400 to 700 nanometer. As we know, we cannot investigate beyond half the wavelength of any probe. So, therefore, the object which we can distinguish by using a polarizing microscope or a light microscope is few hundred nanometers. If there are objects which are smaller than that, which need to be resolved, we require a probe which has a wavelength much smaller than that. One of the such electromagnetic radiation which is available are electrons. The electrons behave in a dual nature, and as we will see subsequently, their wavelengths vary, but can be as low as few picometers. The scanning electron microscope therefore allows us to resolve the heterogeneities of geological material on a very small scale. Actually, the precursor of scanning electron microscope was a transmission electron microscope, which means what is that initially people and physicists experimented with a thin sample. By thin sample I mean that the beam of electron which can pass through that sample, which means very thin sample. Then in 1938 von Erdrine added a scanning coil to this transmission electron microscope, and that can be considered as the original or the first scanning electron microscope. What is actually meant by a scanning electron microscope is that you are doing a real time scanning, which means normally that you have a CRT or a cathode ray tube attached, where you are rastering an electron beam over the object of examination, and real time you are seeing the effect of the electron beam on the matter. So, we come from this to what happens when an electron beam interacts with matter, because that is what is allowing us to have a look or peep into the material which we are seeing. As far as the SEM is concerned, two major kind of things happen when an electron beam interacts with matter, and these things can be classified in two ways. That is, we can call them as scatterings of the incident particles, which can be either elastic or inelastic. By scattering, by elastic scattering, I mean that the energy of the incident electron beam remains unchanged or more or less unchanged. By inelastic scattering, the large part of the energy is spent. To quantify this, we can look at this in real terms. In scanning electron microscopes, the kind of energy which we employ are of this order: 10 or 20 kilo electron volt. Now, this numerically is same as the potential difference which is applied to generate the electron beam, but the unit of that is kilovolt. So, 10 kilovolt or 20 kilovolt potential will lead to the emergence of an electron beam which will have unit of kilo electron volt, but numerically it is similar. Now, if this beam interacts with any matter and the incidence direction is changed, for example, if the beam is coming like this, interacting with matter, and the direction of interaction changes and the beam moves or the electron moves to a different direction, that means there is a significant change of direction, but there is no significant loss of energy. The significant loss of energy would be if this beam becomes few electron volts. So, therefore, if it is 90 to 95% same energy, then we call that as elastic scattering. In the other case, when this incident electron beam may not change its direction, but loses most of its energy and is in the order of now 5 to 100 electron volts, then that will be an inelastic example of an inelastic scattering. So, these are the two main kinds of change which occur in an incident electron beam, but it produces multiple effects which are of tremendous use in microscopy. And since we are today discussing mainly the microscopy, so we will concentrate on that. Let us first look at the elastic scattering. Elastic scattering can be expressed in this form, is proportional to z square by E square, where Q refers to the probability. Now, following Heisenberg's principle of uncertainty, the simultaneous definition of position and energy of atomic particle is not possible. So, therefore, the interaction of the electron beam with matter can be best described as a probabilistic event. So, the probability of a elastic scattering is expressed in these forms, where E is the energy, Z is the atomic number of the material with which the electron beam is interacting, and Q refers to the probability of an event occurring. Now, the elastic scattering will be higher for higher Z or higher atomic number element, which means that if we have a recorder which can record the scattered electrons, then for higher atomic number it will record higher number of electrons, for lower atomic number lower number of electrons. And if we get this in form of a gray tone image, we will be able to distinguish the brighter parts as higher atomic number. In case of compounds, we can have a average atomic number. For example, that can be expressed as average atomic number equal to sigma Ci Zi, multiplied by Zi, which means that the concentration of an element I multiplied by the atomic number of that particular element. To illustrate this, let us look at this formula of Plagioclase-Feldspar known as Albite. Now, in this, if we have concentration of sodium, aluminum, silicon and oxygen, and that fraction of concentration is multiplied by their atomic number, that is Z of Na, Z of Al, etc., and we sum that up, that will represent the average atomic number of Albite. And if an Albite and magnetite are present together, then magnetite will appear as brighter because its average atomic number is higher. So, this function allows us not only to distinguish different phases of different composition, but it also allows us to distinguish variation of composition within a phase, and one can pick up zoning in this. At the extreme end of this, even 0.1 atomic number differences can be picked by a scanning electron microscope. The amount of elastically scattered back electrons in proportion to the incident electron is known as the backscattering coefficient. This phenomena of elastic scattering is called as backscattering. And the amount of backscattered electrons in reference to the incident electron is the backscattering coefficient. So, higher atomic number elements, minerals and compounds have higher backscattering coefficient, and it is a very useful tool to distinguish petrologically different phases and variation in composition within the different phases. This is one important microscopy function which is obtained through scanning electron microscope. The other thing which happens is the inelastic scattering. Now, inelastic scattering occurs because an incident electron beam passes through several events till such time it loses all its energy. Now, each of these events can be described by an equation like this: mean free path, and it is expressed in form of an equation where gamma, which is the mean free path, is equal to A divided by N0 rho Q. In this, A represents the atomic weight, N0 represents the Avogadro number, rho represents the density, and as we learned earlier, Q represents the cross section of the incident electron beam expressed in terms of area. So, this gives us the mean free path of one event. Till such time an electron loses all its energy, that is, let us say from 10 kilo electron volts to when it comes to rest or 0, it will pass through several mean free paths, and the average path will be a sum of all these mean free paths. Once we look at this equation, the electron will lose its energy differently in different rho or different density material, which can be expressed as, when an incident electron beam is there, it will lose its energy in several mean free path, which can be of this, which can be modeled for different density material till such time it loses all its energy. And if this is modeled for the entire dense material, then the shape of the interaction volume is that of a teardrop shell, like this, and depending upon the density, which is a function of the atomic number, for lower density the volume of the interaction volume space will be more, which means that an electron beam of X energy will penetrate more in a less denser material and will penetrate same energy will penetrate less if the rho or the atomic number is higher. So, therefore, the penetration of an electron beam will be a function of the density normally expressed in terms of atomic number for different quantities. If we increase the energy of this incident electron beam, the penetration will be to a greater depth. So, the two things which control the depth of penetration, or in other words the interaction volume, are the incident energy as well as the density of the material. As you see that interaction is in a volume, and the interaction defines the volume at which the electrons are losing all their energies, incident electrons. When they are losing all their energies, following the law of conservation of energy, that energy will be transferred into some other form, and that helps us as a microscopy function also. We will come to that little later. So, one category of electrons we talked about are the elastic scattering backscattered electron, which are a function of the atomic number and are useful as a microscopy function. The other category of electrons which can emit, which can come out when an electron beam interacts with matter, are known as secondary electrons. These are a result of inelastic scattering, which means that the energy of the secondary electrons is significantly lower, normally of the order of few electron volts and not going beyond 50 electron volts in most cases. Now, those are very useful because they come out from the top surface of the interaction volume, and they define the shape and the figure of the interaction volume, and they are used as a very nice criteria to distinguish at high resolution, and we will discuss resolution subsequently, high resolution the material which we are examining. However, these secondary electrons are not strongly a function of the atomic number of the material. So, therefore, they do not distinguish. If we were to plot a diagram where this represents the fraction of backscatter and secondary electrons, and this represents the atomic number, then increasing in this direction, then the backscatter electron production will be like this, that is, with higher atomic number more backscatter electrons. But the secondary electrons production is generally lower and like a plateau, it does not increases with increasing atomic number. So, it does not distinguishes the atomic number, but it describes the surface features very nicely. Now, we will look at the resolution of the incident electron beam. I mentioned earlier that the investigation by a beam is related to its wavelength, that is equivalent to half its wavelength. Now, when we try to analyze the wavelength of an electron beam, it can be expressed by this relationship, which relates Planck's constant and momentum of the particle. The wavelength becomes related by this equation. Now, velocity of an electron is dependent upon the accelerating voltage, and if we relate it here, then electron volt is expressed as under root 2 e v by m. Thus, the wavelength of an electron beam can be given as lambda is equal to h by under root 2 m e v. Now, let us try to understand this in terms of certain numbers. Considering that the mass of an electron is 9.1 into 10 to the power minus 31 kilogram, and the charge is 1.6 into 10 to the power minus 19 coulomb, wavelength of electron can be computed as lambda is equal to 6.626 into 10 to the power minus 34 divided by under root 2 into 9.1 into 10 to the power minus 31 into 1.6 into 10 to the power minus 19 into v, and this works out to be 12.25 into 10 to the power minus 10 under root capital V, which represents the accelerating voltage. For an accelerating voltage of 10 kilo electron volt, the wavelength of electron beam works out to be 12.25 picometer. As you can see, this is significantly lower and provides much higher resolution than optical microscope. And for an 100 kilo electron beam, it is 3.87 picometer. The maximum resolution of a probe behaving as wave is generally up to half its wavelength, and thus detailed examination by a scanning electron microscope of the order of few picometers is eminently possible, which is the strength of a scanning electron microscope. However, we must remember that the interaction is not only from an area, but as we learnt earlier, from a depth or from a volume, and the extent of the volume depends on the nature of geological material, that is inversely proportional to the density and directly proportional to the incident electron beam energy, and that defines the resolution in terms of volume, not in terms of area. Other than the secondary electrons, the other major effect of the inelastic scattering is generation of X-rays. Now, these X-rays are of two types. One, the characteristic X-rays, which means that they refer to a particular energy level transition within a particular atom, and the other, a continuum of X-rays, which represents the background material, and we need to know both if we were to characterize the chemical heterogeneity in a material. The characteristic X-rays produce a very good effect to chemically quantify the nature of material. Now, in this diagram we can look that from which part of the interaction volume which effects comes. As you can see, this is the surface where the electron beam is impinging on the material. The characteristic X-ray are produced as a result of the inelastic scattering. So, they come from the lower half of the interaction volume. The upper half produces the backscattered electrons. The characteristic X-rays are produced when the incident electron energy is over a certain critical limit or critical excitation energy. So, the characteristic X-rays are defined in terms of the critical excitation energy. The continuum X-rays are produced all through. They start from the upper part, and where the incident electron energy has lost all its energy and is converted to the X-rays up to the bottom. So, the continuum is produced throughout the volume, and besides these there is an effect that the characteristic X-rays can sometimes produce or can lead to a secondary X-ray which is known as fluorescence. So, secondary fluorescence by continuum as well as by characteristic X-rays can also be produced, and that also can occur throughout the volume of interaction. So, we see that this complex domain produces different kind of X-rays. Besides these effects, there is a generation of Auger electrons. The Auger electrons occur when an expelled electron from an atom leads to, if it has high enough energy, expelling of another electron, and those are known as Auger electrons, and that can also be used as a characterizing tool for material. So, several of these effects ultimately contribute to the complex result, and one can catch each of these in form of individual characterizing effect as a microscopy function. Let us look at the images produced by backscattering as well as those produced by secondary electron, because the SEM has main function of microscopy. In this figure, which is a very interesting figure, one sees towards the right hand side a garnet which is actually breaking out or breaking down to two phases, and these phases are orthopyroxene and plagioclase. This is a typical texture which is known as symplectite. Other than the plagioclase and orthopyroxene being produced as worm like structures in this figure, one can also notice the iron oxides which are present in between, which were possibly produced as excess iron when garnet broke down, which is because it appears to be a high iron garnet. So, the SEM allows us to distinguish, that is the backscattered electron image allows us to distinguish the breakdown reaction very nicely, and also allows us to chemically characterize the product which are being formed. In this figure, which is typical of an igneous texture, we have exsolution of pyroxenes within pyroxene, and again the backscattered electron image allows us to distinguish not only one crystallographic layer along which the exsolutions have taken place, but at an angle there is a fainter shade which is distinguishing two different events of exsolution. As the backscattered electrons image, that is an elastic scattering event, distinguished the composition, in this figure the inelastic scattering leads to generation of excellent image where the microfossil ornamentation and parts are detailed. In the first figure we see a relatively larger sized image which is magnified in the second diagram, where the marine microfossil is illustrated very nicely, and one sees the distinguishing features of the fossil nicely outlined as a result of secondary electron image. You can see that this is at 5000 magnification, and one can achieve significantly higher magnification for resolving these images, which are not possible by an optical microscope. Inelastic scattering also produces long wavelength radiation in the visible range as well as in IR and UV range, and these spectrum produce very useful images of cathode luminescence. Now, in these two figures, the cathode luminescence produced images of zircon are seen, and one can distinguish different stages of growth in zircon as well as some included particles in zircon, and one can distinguish the magmatic and the metamorphic. The thin bright images rims in both the grains represents the metamorphic growth, whereas the inner oscillatory zone images represent a magmatic event. So, the cathode luminescence, which is an inelastic scattering effect, allows us to distinguish events like this in zircon and many other minerals. For chemical characterization, the relationship between the wavelength of a characteristic X-ray and atomic number was empirically established by Moseley in 1914. It stated lambda, that is the wavelength of characteristic X-ray, is proportional to the atomic number with a proportionality constant. Now, this is utilized, the wavelength is utilized in form of Duane-Hunt equation, and once we apply that, the illustration can be seen in this backscattered electron image, which also has the characteristic element X-ray spectra of different minerals. This figure is from the Khetri mine, and in this, in the center we see chlorite, which is reflected by the presence of iron, magnesium, silicon and aluminum, biotite, which is a left-over phase indicating that the chlorite formed by the alteration of biotite, and the characteristic spectra of biotite includes besides iron, magnesium, potassium also, signifying that it is distinctly different, as well as it has a different backscatter signature, that it is brighter than chloride. And then at one corner of this figure we find that there is a relic garnet. So, it is not only that the biotite produced chloride, there is a relic garnet, suggesting that the earlier peak assemblage was garnet and biotite together, which produced subsequently chloride and muscovite. So, the combined backscatter image and the characteristic X-ray data allows us to distinguish not only the material, but also allows us to work out the reactions which have taken place in geological material. So, we see that a scanning electron microscope allows us to distinguish and resolve the geological material at significantly higher level, not only in terms of as its microscopy, but also in terms of its chemical entities. It allows us to distinguish detailed morphological features of fossils and other material. It also allows us to distinguish the zoning which is observed through the visible light and other effects, and it allows us to interpret the magmatic and metamorphic history of a rock. Thank you.